Let me give you two theorems about the differentiation and the continuity. If f has a derivative at x equals c, then f is continuous at x equals c. Proof. Limit x equals to c, okay, f of x minus f of c, it equals to limit x equals to c, okay, x minus c times, okay, f of x minus f of c. I've just multiplied by the x minus c both sides of the factor, which is numerator part and the denominator part, okay, x minus c, and after that I can say limit x equals to c, x minus c times limit x equals to c, f of x minus f of c over x minus c, and the left part will be 0 times f prime of c, it equals to 0, okay, if, okay, f prime of c is finite, okay, and whenever f prime of c exists, the total limit is 0. Okay, and the result of this proof, I'll give you another theorem, which is the very popular theorem. Listen me carefully. Differentiable functions are continuous. And please caution, continuous function need to be, I'm sorry, need not to be, of course, need not to be differentiable. Okay, popular example about this quotient, okay, and we know that f of x equals to absolute value of x. It's a continuous function at x equals to 0 point, right? Okay, but the f prime of 0 does not exist. Sketch it. Okay. this is absolute value of x, okay, we know that, and the f prime of x this is the f prime of x. As you see, at this point f prime of 0 does not exist, so don't forget it. We can say differentiable functions are continuous, yes, but continuous function need not to be differentiable, okay? Sometimes you can find some continuous functions, yes, they can differentiable, but some of them cannot be differentiable, okay? Don't forget it. The mean value theorem. Assumptions f is continuous on a comma b close interval, and f is differentiable on a comma b then there exists a point x equals c such that c element of a comma b open interval and such that f of b minus f of a over b minus a equals to f prime of c. Okay, and for example, okay, and maybe this part will, yes, here is point A and here is point, I'm sorry, this is point B and this is point A, okay, and right, okay, and this is our f function, which starts from a to end for the b point, okay, and this is y equals to f of x, right, and when you connect this a and b point, okay, as you see, and by theorem says us, okay, and you can find any c point, okay, and it will be equal to, okay, your tangents, your slope of the tangent, okay, and that means that, for example, okay, and as you see, this is your C point, okay, and this point is FB minus FA, and this black dotted lines is B minus A, right? And as you see, this tangency are same, so M equals to, for this green line, okay, FB minus FA over B minus A, okay, and we know that F prime of C equals to this slope, okay, so as you see, A is less than or equal to C, C is less than or equal to B. We have just found a C point such that which is on the A comma B open interval, and this point equals to F prime of this C point equals to FB minus FA over B minus A, which is the slope of the tangency of this curve, okay, and this is the mean value theorem, okay, and by using this theorem we will solve lots of problems in future, and particularly let me give you increasing and decreasing functions, okay. F is defined on I, which is interval, okay, any x1, x2 element of I, okay, definition A, okay, and the A says us if f of x1 is larger than f of x2, whenever I'm sorry, not whenever, of course, wherever x2 is larger than x1, then let me write these parts again, okay. F of x2 is larger than f of x1, okay. Wherever x2 is larger than x1, then we can say f is increasing, okay, on that interval, okay. And the part B, if f of x2 is less than f of x1, okay, wherever x2 is larger than x1, then f is decreasing on I, okay. For the part A, okay, this is B point and this is A point, okay. Okay, for example, this point is x1 and this point is x2, okay. And and this is f of x1 this is f of x2. As you see, f of x2 is larger than f of x1, okay, wherever x2 is larger than x1. So this function is increasing on, okay, a comma b interval, we can say that, okay. And this is for part B, and now maybe this is A point and this is B point. Okay. And okay, what can we say? For example, when you choose here x1 and x2, okay, this is f of x1, this is f of x2. As you see, f of x2 is less than f of x1 wherever x1 is less than x2, right? So we can say for this function decreasing on a comma b close interval. Okay, and the AB. Let me continue with the definition part C. Yes, definition part C. If f of x2 is larger than or equal to f of x1, wherever x2 is larger than x1, then we can say f is non-decreasing code on I. Okay, and some of you can understand, but some of you want to see on the graph, okay, maybe, and let me sketch it. For example, this is B, this point is x1, this point is x2. Yes, as you see, x2 is larger than x1, okay, but f of x1, f of x2, it equals, so we can say f is non-decreasing on this interval. Okay, we can say that because we have just found any 2 points such that x2 is larger than x1, but we couldn't say f of x2 is definitely larger than x1, f of x1. So we can say for this kind of curves, okay, non-decreasing curves, okay, we can't say, okay, increasing, but we can say non-decreasing, okay. And by the same idea, if f of x2 is less than or equal to f of x1. Okay, whenever x2 is larger than x1, then we can say f is non-increasing on that interval. Okay, let's continue with the theorem about increasing and decreasing. Assume that f is continuous and differentiable on I, and the part A, if f prime of x is larger than 0, that means every x element of I interval, then f is increasing on I. B, if f prime of x is less than 0, every x element of I, then f is decreasing on I. C, if f prime of x is larger than or equal to 0, every x element of I, then f is non-decreasing on I. And the part D, if f prime of x is less than or equal to 0 for every x element of that interval, then we can say f is non-increasing on I. Example, y equals to f of x, so it equals to x cubed minus 12x plus 1. That function is continuous and differentiable for all x in the real plane, because of that's the polynomial function. Okay, and the y prime equals to f prime of x, it equals to 3x squared minus 12. Okay, and it equals to 3 times x squared minus 4. Okay, and it equals to 3 times x minus 2 times x plus, x plus 2. And we know that on the number line, okay, and on the real line, minus 2 and the plus 2, which are the factor of this y prime, okay, and the x, we know that y prime will be larger than 0 at this part, and for this part y prime is less than 0, and again y prime is larger than 0, and we have just found the larger than 0 point, okay, and so we can say increasing for this part, decreasing on the interval -2 to the +2, and here increasing again, okay, and let's assume that this function will be like that. This is only symbolic function, okay, and not the truth function, not the true function, okay. This is +2 and this is -2. As you see, at this part from -infinity to the -2, this function is increasing, okay, and from -2 to the +2 our function is decreasing, okay, decreasing. And after this point, from the +2 to the +infinity, as you see, our function is increasing again, okay. That's the symbolic sketching of y function, okay. And then let me give you a Rolle's theorem. Rolle's theorem. Suppose that G is continuous on A comma B and differentiable on differentiable on A comma B open interval if G of A equals to G of B, then there exists C element of A comma B such that G prime C equals to 0, okay. That means this point is B and this point is A. A, B, and the G of A equals to G of B, okay, as you see. This function must be continuous and differentiable on this interval, okay, and as you see, we can find any C point like that, which is the slope of this line, okay, will be equal to 0, okay, and that means the G prime of C equals to 0, okay, and of course this is the y equals to G of X function, okay, and you can find that theorem's proof on your book, and it used the mean value theorem, okay, and please look at the Rolle's theorem proof on your book. Okay, it can be important, it can be useful for you. And let me continue with the 2.7, which is the applications of derivatives. Okay. I'm sorry. Yes. 2.7. Applications of derivatives. Definition: instantaneous velocity is the derivative. Instantaneous velocity, that means the velocity only can be used, okay, it can be possible, of the position with respect to time if S position of a particle then velocity of the particle S, okay, I'm sorry, S equals to S of t, that means with respect to time, S of t, okay, it with respect to time of course, and the velocity of t, it equals to del S of t over del t, that means limit delta t approaches to 0, okay, del S over del t, and which is equal to limit, okay, delta t approaches to 0, okay, S of t plus delta t minus S of t over delta t. Okay. And the example. Free fall displacement we know that S equals to, okay, 1 over 2 g t square, okay, and what was g? You can remember from the physics lectures. G was the gravitational acceleration. Okay, and in USA, G equals to 32 feet over second square. Okay, and in Europe metric, it equals to G equals to 9.8 meter over second square, right? And the velocity, okay, it equals to del S over del T. It equals to G of T, G times T. Okay, I'm sorry, equals to G times T. Okay, and let me give you an example. A dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet over second, and the distance traveled up is given by S equals to 160 T minus 16 T square, okay, and the equals to 0, and the T equals to 0 to 10 seconds, okay, and the part A, how high does the rock go, okay, and the when a dynamite blast blows a heavy rock, okay, and it will straight up from the T equals to 0 time, okay, and after that at the T equals to 10 its travel will be ended, okay, and this is the 10 and this is 0 point, and this is the highest point of the rock, okay, and we will find it, T, and that's the S, okay, and this point is S maximum, okay, and that means the S maximum is reached when S prime equals to 0. Why? Because at this point, okay, the tangency is 0, as you see. Okay, and the velocity equals to del S over del T, so it equals to 160 minus 32t. Okay, and it equals to 0. Okay, and after that we know that the t equals to 5 seconds. Okay, that means this point is 5. Okay, and at the t equals to 5. Okay, and it is the S max, and that means 160 times 5 minus, okay, and 16 times, okay, 25, and it equals to 400 feet. Okay, and this is the 400 feet maximum point, 400 feet. And the B part of the problem: how fast is the rock traveling when it is 256 feet above the ground on the way up. And also on the way down. Okay, and the question is, oops, okay, T1, and this point may be T2, okay, and we know that here 256 feet, okay, and this curve is symmetric curve, and so that on the way up and on the way down, okay, only their seconds will be changed, so it's not hard to solve this question. Okay, and that means the S equals to 256, so that means 256 equals to, okay, 160t minus 16t square, right? And after that means when you simplify it, okay, t minus 2 times t minus 8 equals to, okay, 0, and after that we can say t1 equals to 2 seconds, okay, and for this velocity of t1 it equals to 160 minus 32 times t, and it is t2, it equals to 96 feet over second, okay, its velocity. And when t2 equals to 8 seconds, okay, and the velocity of t2 equals to 160 minus 32 times 8, so it's equal to minus 96 feet over second. Okay, as you know, that means, okay, on the way down, and that means way up.